Okay, so let's go ahead and get started. If you've looked at the homework for the weekend, it might at first seem kind of long, but then you realize that it's actually just the classwork that we did yesterday. So going through the classwork yesterday, I noticed that we didn't do that great, and I don't blame you guys for that. I think that there are things that I can do a little bit better. So we're actually going to take an extra day. I had originally planned to do Gauss's law for 2 days. We were going to do it for 3. And I'm laying out almost exactly how it is that you approach every problem with Gauss's law here for both insulators and conductors. So as you're going through these problems, especially for class today, I actually have it in the question itself to do these steps as you're going through it. For the homework, do the same thing. So like I said, the homework is actually the same as the classwork yesterday. So I wanted to go through those problems again because it seems like a lot of people had some difficulty with it. So to start out with today, I'll do the homework. I'll make a video this afternoon for the homework, but I really want to get into using this process and showing you how to do these calculations for Gauss's law. So I'm going to consider some example here where I have some uniform charge. Let's say that this is some, let's just call it some capital Q, that has some radius of A, and we're going to put some shell around it that has some radius of, inner radius of B and outer radius of C. And we'll put some charge, I don't know, let's say minus 2Q on this. So this part on the inside is going to be an insulator, and this part on the outside is going to be a conductor. And so what we want to do is we want to find what the electric field is everywhere. So looking at, if you look at the homework, it has on the front page exactly the steps that we have here. So I'm going to try to follow this as we're going through. So the first thing that we want to do is to define the regions where we need to find the electric field. And so the regions that I'm going to have here are R is less than A, R is greater than A, R is greater than A and less than B. R is greater than B and less than C, and R is going to be greater than C. Okay. So now for each one of these regions, we want to draw some Gaussian surface, and that's going to end up helping us find what the charge is on the inside. And so we can draw our Gaussian surfaces for each one of these regions. And then there's one on the outside. And I guess because I'm using Gauss's law, the first thing I should really do is write it down. So this is Gauss's law. Okay, so now that we have the regions, we want to evaluate the left-hand side of Gauss's law. So this is something that's spherically symmetric, and we've gone through the whole process of showing how E and ds are going to be in the same direction. This is going to just reduce to E times S, which in the case of spherical symmetry is just going to be E times 4 pi R squared. Okay. Now, the next thing is, if necessary, find rho. So I'm going to start with this R is less than A case, and I have some charge density that's evenly spread over this volume that has some radius of A. And so that means I'm going to need to find what rho is for R is less than A. So by definition, if rho is formed by evenly spreading some charge, it's going to be the total charge divided by the total volume. And here, the total charge is Q. The total volume is the volume that goes up to A. And so this is going to be Q divided by 4/3 pi A cubed. Okay? Everybody with me so far? Yeah.
When do you need to find rho and when do you not?
You need to find rho if I tell you that there's some charge that's evenly spread over an insulator. Otherwise, like for example in the problems that I gave you today, so the first problem I tell you explicitly what rho is as a function of R, right? So in that case I don't have to find rho. I know what it is. I tell you what it is. It's kind of the same thing when we were doing finding the electric field from a continuum of line find charge. So I could tell you what lambda is. I could say like lambda is some function of x or some function of y. Or I could tell you that there's some charge evenly spread from A to 2A, right? And in that case, I needed to find what lambda was. But it's really the same idea here. If I tell you there's some charge evenly spread, find what rho is, okay? So now we have rho. We want to consider the volume of the charge enclosed by the Gaussian surface in this region where r is less than a. Okay, and so here's, let me outline my Gaussian surface again, and it'd be nice if I had some colored chalk. So we can see that this is the Gaussian surface that I'm drawing here. And so its volume is going to begin at r is equal to 0, and it's going to go up to the variable r, right? So that's going to have to do with our limits of integration. So now what we can do is we can find what Qn is here by saying that Qn is just going to be equal to the integral of rho dv. And so this is going to be equal to, I'll put these guys somewhere else later. This is going to be equal to the integral of q divided by 4/3 pi a cubed. What is dv for spherical coordinates? Remember?
4/3 pi squared. It's 4 pi squared.
4 pi r squared. Good. So this is 4 pi r squared times dr. Yep. Good. Do we know why this is? It's interesting when you think about it, because what am I doing here? I'm trying to make infinitesimal volumes, and what I have is some surface area times some infinitesimal radius. So really what I'm doing is I have all of these spherical shells that add up on each other, and that's how I'm actually building this dv. Okay. So now, I already talked about where the charge starts and where it ends, so this is going to go from 0 to r. So I can evaluate this integral. What I end up having is this is going to be q divided by 4/3 pi a cubed times 4/3 pi r cubed. We can cancel our 4/3 and our pi, and so what we see is Qn is going to be q r cubed divided by a cubed. In this region, r is less than a. Now, the last thing that we need to do is we need to find what the electric field is just by putting the rest of this together. And so that's to say that E 4 pi r squared is equal to q r cubed divided by a cubed with an epsilon naught in the denominator, right? Because we have the epsilon naught here. So we can rearrange this, and what we find then is that the electric field is going to be equal to, this is going to be q r divided by 4 pi epsilon naught a cubed in the r hat direction, right? We can recover our vector by considering the fact that we chose ds that was pointing radially outward to start with. Okay, so that's the first region. The second region, we can actually do this one of two ways, because we know already what that charge is on the insulator, and so when we're looking in the region r is greater than a and less than b, what should Qn be? Just intuitive. Count up how much charge is in there. A couple of different ideas. Somebody say something a little louder.
Q.
Q. Why?
Because it covers the whole volume of the...
Yeah. That Q that I evenly spread over the insulator, now that's entirely inside the Gaussian surface that I drew in this region, right? And we could prove that actually if we wanted to do this with an integral. So how would our integral change here? Well, rho is still the same, right? I'm still talking about the same insulator, the same distribution of charge. So rho is the same. So this is still going to be the integral of 4/3 pi a cubed. And then the dv is the same, right? What is going to change? My limits of integration. What are they going to be now? It has something to do with that, but think about what the limits of integration mean. Maybe. So when I'm talking about adding up these little bits of charge, I'm thinking about where does the charge start and where does it end? Where does this distribution of charge start? 0. Where does it end? Still looking for the, what's the largest value that, of the radius that this charge goes up to? Think about the insulator that I have. The insulator is just the inner sphere. A. It goes up to A, right? Do we see that? So look, this is the Gaussian surface I'm dealing with, right? I want to find what the charge is on the inside. I can either just say, well, it's just the total Q that I have here, or I can say that if I want to integrate this to find Q is equal to rho dV, I need to think about first what rho is. We know what rho is, and we know what dV is. So the tricky part is the limits of integration. And what the limits of integration tell you, and this is a very important thing for the physics, what are the limits of integration telling you? They tell you where the charge starts and where it ends. So for the first case, the charge started at 0, it went up to this R, right? For the case where I'm trying to find the electric field in the region between A and B, the charge starts at 0 and it goes up to A. Yeah?
So our upper bound will never be the edge of the Gaussian surface?
It will be when you're inside the insulator.
Okay,
right?
So between R and A in the situation is that R needs to be less than A to make sure it's inside that field?
Yes. So if R is less than A, then my limits of integration go up to R because I'm trying to find what this charge is, right? And that's only going up to R, right? It doesn't go up to A because going up to A is outside of what R is for this region, right?
Because it cannot equal A.
Yes, it can't go up to A because A is outside the Gaussian surface. Yeah.
If when we're inside the insulator, we're allowed to go to the edge of the Gaussian surface when we're evaluating the integral, then why do we evaluate from 0 to R instead of 0 to A?
Because 0 to A is going to give you charge that's on the outside of the Gaussian surface. Remember when I'm defining Q in.
Go to 0 to A.
What's up?
So if it was a conducting surface, you go to 0 to A.
No, the conductor is going to be different. I'll talk about the conductor when we get to this outside piece. But the conductor, the thing about a conductor is the electric field on the inside is always 0. So it's actually easy to evaluate this. I can say that just by definition, the electric field between B and C is 0 because it's a conductor. But what that allows us to do with Gauss's law is it allows us to find what the surface charge density is. Because if the electric field in this region is 0, that means the charge inside has to be 0. There's charge here, there's charge at the surface, and so whatever this charge is, it needs to balance with what this is. Yeah. Other questions? This is important. I think this was the part that was tripping the most people up. Yeah.
So when we're defining limits, I'm just making sure that I'm understanding right. So our upper limit isn't particularly just like the radius of the Gaussian circle. It's just the radius, I guess, of the charge distribution within that. Like how
exactly.
can I go and still be on this charge?
Yes, exactly. And that's why for when I'm inside, I'm going up to R because that's the furthest it is.
Okay.
And then when I'm outside, I'm going up to A because this charge doesn't go up to R. It only goes up to A. Okay. And what we can do is when we look at this calculation here, when I integrate this from 0 to A, and this is a good check. Always with physics, if you have multiple ways to approach a problem, they should give you the same answer. Well, if I do this integral, I'm just going to get a 4/3 pi A cubed from this, and that's going to cancel this one, and I lost my Q here. There should be this should be divided by Q divided by this. Okay, because that's what rho is. Rho is Q divided by 4/3 pi A cubed. I didn't make that mistake up there. Okay, good. So this is just Q. Okay. And this is probably one of the harder parts about Gauss's law, talking about insulators and talking about what the charge is on the inside of insulators. And making sure that you understand what my limits of integration are and why those are the limits of integration. You should always think that Qin is the charge that's contained inside the Gaussian surface, and in order for that to be the charge contained inside the Gaussian surface, does my limit go up to R or does it go up to A based on which Gaussian surface I have? Okay. Now, what I did yesterday, and it was probably a little bit too much at the time, I had a hollow piece, right? Remember how I had a hollow interior? Well, that's just going to change my lower bound, right? Remember that? Question?
So is the idea that because we have a distribution of charge in the middle that occupies some volume, the q r cubed over a cubed can represent the charge inside of any radius in that charge density, but because there's no charge in that outer band, no matter where we are in that outer band, it's always going to be the same amount of charge?
Yes. Yeah, because if I'm at some variable radius less than the total, I'm not enclosing the whole charge. And that's what I'm doing when I'm taking into account that here when I'm doing this integral, is that I'm adding up all the pieces that go up to there but not past it. Okay. And then when I'm out here, I have the whole thing.
So the extreme edge of that charge region, you would plug in A and you just get Q, which would be the same as...
Exactly. Okay. Yep. And that's kind of what I proved here by explicitly doing the integral. This follows exactly what you would expect if you said, well, what is the charge inside there? It's just Q.
The charge that's in there.
Yep.
You said. Okay.
Yep. Okay. So that's R is between A and B. So this is just Q, and so actually to evaluate Gauss's law here gives us something pretty nice, because Qn is just Q divided by epsilon naught, and so this is actually just our familiar electric field due to a point charge. Okay. Is there a question? No. Okay. All right. So now the easy part. What is the electric field between B and C? I already kind of answered this one. Now we're in a conductor. What's the electric field in a conductor? 0. Good. E is equal to 0. But this allows us to say something, right? Because if the left-hand side of Gauss's law is 0, then the right-hand side of Gauss's law is also 0. So if the electric field is 0, Qn is 0. So what does this allow us to do? What can we do with this piece of information when we say, draw this Gaussian surface, the electric field is 0, that means Qn is 0. What can we do with that? Has something to do with the conductor.
Put the charge on the surface.
Yes.
That is your charge.
We can say that the charge at this surface the total charge inside this Gaussian surface is going to be the charge at the surface plus the charge at the center. Yeah.
When you're saying the surface, are you referring to the surface at B or the Gaussian surface?
The surface of the conductor at B.
Okay.
Yeah, because the way that conductors work, charge can flow in them, right? And so what's going to happen is, because the electric field is 0 on the inside of the conductor, charge is going to rearrange itself to be on the surface. So conductors always have charge on the surface. Insulators can have charges inside and distributed in different ways. But for conductors, it's always going to be on the surface. So what that allows me to say more precisely here is Qn is going to be equal to 0, which is equal to Q at B, plus the Q at the center, which is Q. Okay. So this says that QB is equal to minus Q. Okay. Now, what else, now that I have that information, now that I know QB is equal to minus Q, what else can I say? What else can I say? Well, I know there's some total charge of minus 2Q on this conductor.
So the charge of the outer surface is also minus?
Yes. Yes. And so what we can do to see that is we can say that the total charge on the conductor, because the charge on the conductor is only going to be on the inner or outer surface, can be written as the charge at B plus the charge at C, right? Now we know what QB is. We know that that's minus Q. This is minus Q. We know that the total charge on this is minus 2Q. And so we can write some algebraic equation, and we can actually just see that in order for this to be true, then QC is equal to minus Q. Okay. And from this, if I asked you what the surface charge density is, you would just take the charge of that surface divided by the surface area of that surface. So if I wanted sigma b, then we would say that would be minus q divided by 4 pi b squared. Okay. Now the last part is to find what the electric field is for r greater than c. Okay. And to do this, again, we have our left-hand side of Gauss's law. We just need the right-hand side. So ultimately, that's going to come down to what is q in. So I draw the surface all the way around the outside here. What is the total charge that's inside that surface? I don't know what I'm stepping on.
Wait, no.
Why negative q? Yes, because we have, you had the right answer. I just wanted to make sure that you knew why. So we have this q plus q in the middle, and this conducting shell has some total charge of minus 2q, and so q in is just going to be the sum of the total charge that's on the inside of the Gaussian surface. And so that says here that this is going to be minus 2q plus q, which is equal to minus q. Okay? And then we can rearrange this and then see that the electric field E vector is going to be equal to 1 over 4 pi epsilon naught times minus q divided by r squared times r hat. Okay? And that's it. Any questions about this? Like I said, we're gonna spend an extra day, and I think if things are still not clicking for you, hopefully by the end of Monday they will. And I think we'll probably do some more of these kinds of questions in recitation still too. Okay. Yeah.
Why can you assume that the charge is 0 at the inner surface? I mean, at B? Or not at the inner surface, but between on the inside body of the conductor?
It's something just by definition that the electric field is equal to 0 on the inside of a conductor. Now I could show that more rigorously with using what's called the microscopic form of Ohm's law, which is something that we'll do next week. But we know we've seen V is equal to IR probably, right? Well, this comes from what's called the microscopic form of Ohm's law, which says that the electric field is equal to the resistivity times the current density vector. Now, for a perfect conductor, the resistivity is 0. But that also, the other way that you can see this is, if this is an equilibrium, none of the charge is flowing, right? So none of the charge is moving from here to here, so the current density is also 0. So the electric field is 0 actually because both of these are 0. Okay. All right. Yeah.
This is going to be the easiest question. What question number did we just do? Was that?
I just made this up.
Okay.
I just made this up.
Okay.
Yeah. Okay. Any other questions? Okay. So let's get to work on the classwork for today. Like I said, I tried to stratify this so that it's very step by step. And I hope by doing this it'll make a little bit more sense how to do it.